The next thing that I'd like to do is I'd like to move away from integral domains and move into what's called a field and give the definition of that. So remember that when we were doing the definition of an integral domain, we added on some requirements from what we required of just a ring. We threw on that we definitely wanted our multiplication to have an identity, but we did not require that every element have a multiplicative inverse in that last of those four group properties. What we can instead do is we could say, what is it when we go all the way? We were already requiring that our group, that our ring have a group structure under the addition operation. What if we also require that our group, our collection of things, be a group under the multiplication structure? And when we do that, what we get is the definition of a field. So a field F is an integral domain where all non-zero elements are units. So we don't worry about zero. We don't need zero to be a unit. That's not going to be possible for us, just like it isn't with the real numbers or the complex numbers. Zero doesn't have a multiplicative inverse, but everything else does. And in fact, these are our most familiar examples of things that are fields. So the integers are not a field, as we discussed a little bit earlier. Plenty of things in the integers do not have multiplicative inverses. The integers are not an example of this. One example of this, though, however, is that z mod pz is a field when p happens to be a prime number. So z mod pz was an integral domain when p was prime, but it's also going to turn out to be a field. And our very familiar examples of fields, the ones that we're used to working with all the time, are the rational numbers, the real numbers, and the complex numbers. These are fields because when you take away the zero element, everything has a multiplicative inverse. And for a less familiar example of something that is a field, or an example that's a little bit harder to work with, when we take the rational numbers and we join root 2, what we're going to end up with still is a field, actually. Now, we saw that z mod pz is an integral domain, but in fact it also turns out to be a field, or that's what I'm claiming. But this is an example of a more general phenomenon. The lemma that we're going to prove right now is that if D is a finite integral domain, then D actually turns out to be a field. So that's true of the integers mod p. Those are a finite integral domain, and so they're automatically a field by this lemma. And let's see how the proof goes, because this is a nice example of how we work with things as fields. So we're assuming that D is a finite integral domain. So let's let n be the number of elements inside the set D. If A happens to be an element of D and A is non-zero, then what we need to do in order to show that D is a field is show that A has some sort of multiplicative inverse. So to do this, here's the trick. What we want to consider are n different powers, the first n powers, of the element A. So a to the first, a squared, all the way out through a to the nth power. And here's the key observation. There are n elements in D. One of those elements is 0. The a that we picked is definitely not 0. And since D happens to be an integral domain, again by hypothesis, we know that there's not a power of this element A that happens to be 0. I mean, if a to the I were equal to 0 for some positive integer I, then what we would wind up with is a zero divisor. A times this a to the I minus 1 would be equal to 0, and we'd have some zero divisors. Okay. So there are n minus 1 elements of D that are non-zero, and what we're saying is that a to the first, a squared, all the way out through a to the nth power, that none of those elements is 0. And there we have n elements, a squared, all the way out through a to the n. We have n non-zero elements of D. So by the pigeonhole principle, there's too many powers that we're looking at here for each of them to be distinct, which means that there are powers, there are integers, I and j, that are different. I and j are not the same, and yet a to the ith power must be equal to a to the jth power. That is, one of the elements in these, we have to have some repetition going on. When we look at a to the first, a squared out through a to the n, there has to be a repetition of the elements of D. So we take the two that are the same, or at least two that are the same. They're different powers of A, and yet they're equal. Now, all we know about the integers I and j is that they're not the same integer. and therefore one of them is bigger than the other. So what we're going to do is we're going to write W log, which means without loss of generality. And we're going to suppose that I is the integer that's larger than j. So whenever we're comparing two integers that aren't the same, then one of them is going to be bigger than the other. From the equation a to the ith power is equal to a to the j, we're going to apply cancellation j times, the smaller of the numbers, so that when we have this cancellation, what we're left with on the right-hand side is just the number 1, and what we're left with on the left-hand side is a to the I minus j, and that I minus j is a positive integer since I is bigger than j. So what we've done here is we've taken a and we've raised it to some positive power, and we've gotten the identity. If we peel off one more copy of the a here, we write a times a to the power I minus j minus 1, then what we've done is we've found a multiplicative inverse for a, namely a to the I minus j minus 1, and we're done. We've found that multiplicative inverse for a was an arbitrary element of the integral domain, thus proving that D is also a field.